So negative angles. Sine of a negative angle would have the exact same value as negative sine of the positive value of that same angle. So sine negative theta is equal to negative sine theta. And then for cos of negative theta is the same as cos theta. So it's worth just memorizing that this is how it works, and once you've practiced enough, you just know this automatically. But I think a good way to understand why these two statements are actually true is by seeing the graphs of sine and cos plotted for both positive and negative angle values. Starting with the graph of sine. So that's how the sine function looks, where on the x-axis you have angles in intervals of 45 degrees, so you have 0 up to 360. And then also the same values but the negative version of them. And what you'll see is that for any particular angle, now this will be true for all angle values, but we can look at a few different examples. So let's try 90 degrees. So if you take theta as 90 degrees, then sine of negative theta, meaning sine of negative 90, has the exact same value as negative sine of 90. And then we can try another value, let's say 45 degrees. So sine of negative 45, we can see here it's a little less than minus 0.5, so this is roughly minus 0.6 something. So sine of this negative 45 is roughly negative 0.6 something, and then this would be the same as negative sine of positive 45, meaning positive 0.6 something. So the visual way to understand why sine of negative theta is equal to negative sine of theta is the graph of negative sine is exactly the same as the graph of positive sine, except it's reflected about the x-axis. So when you reflect something about the x-axis, values above the x-axis are positive, and on the other side they're negative. So sine of a positive angle will be the negative of the sine of the negative angle. Then for cos theta, why is cos minus theta exactly the same as cos theta? Let's look at the graph. So that's a graph for cosine. As you may notice, the cos graph is basically symmetric about the y-axis. So the graph for positive angle values looks exactly the same as the graph for negative angle values, and that is why cos of theta is equal to cos of negative theta. You can check it again. So say with cos of 90 is 0, which is the same value you get for cos of negative 90. Then cos of 45 is about 0.6 something, and cos of negative 45 is also 0.6 something. So that's sine and cos of negative angles. So what about tan? So I want to show you the graph, but basically tan of a negative angle is equal to negative tan of the positive value of the same angle. So it's basically shows the same trend as the sine function. And I would say in general, a useful way of thinking about tan and the way the function behaves is always just to think about it in terms of the quotient identity, meaning it behaves as a result of what happens when you divide the sine function by the cos function. So tan of negative theta would be sine of negative theta over cos of negative theta. Then sine of negative theta becomes negative sine theta, and cos of negative theta just remains as cos of theta because of this whole symmetrical aspect. And then the result is just negative tan theta. And that's how the three functions of sine, cos, and tan behave for negative angles. Then the last portion that we need to revise is 4 quadrants. And this is a section that a lot of students, including myself back when I was in high school, find really confusing and difficult to make sense of. And that's why even though it's the last part of the revision section, it'll actually be relatively long because I want to dedicate some time to it so you can completely make sense of it and be comfortable with it going forward. 4 quadrants are a very useful tool for determining what different angles would be the solutions for a specific trig function. I'll explain the idea using an example. Say you're told that sine theta is equal to 0,5, and then you're asked what is the value of theta in the interval of 0 to 360 degrees. then to solve for theta, you just take the sine to the other side and say sine inverse of 0, 5. And this gives you a value of 30 degrees. And is this the final answer? No, because if you were to plot the graph of sine theta and see which theta values give 0, 5, so I've shown it here. So this is the graph of sine theta with theta on the x-axis, and then I've drawn a horizontal line for whenever sine theta is equal to 0, 5. And therefore the answer of the question, which values of sine theta equals to 0, 5, you just see where this line intersects the graph. So yes, for sure, you first get it for a theta value of 30 degrees, but then if you continue a little further, you get that value again for a theta value of 150 degrees. And since, as we can see, the graph just keeps repeating over and over, you would get it for many more angles as long as you kept increasing the value of theta. But here I just stopped it at 360 degrees. So this property of a trig function just repeating over and over many times is known as periodicity. And this occurs for all the trig function graphs, meaning you see the same trend for the graph of cos theta and for tan theta as well. For all of them, indeed, the graph shape will keep repeating over and over again. The main difference between them is, for one, how the graph looks, and two, how often it repeats, meaning after how many degrees does the entire shape of the graph repeat itself. And this value is known as the period. So the period is the angle after which the function repeats itself. For sine, the period is 360 degrees, which you can clearly see here where, say, starting from the very left, we have the graph here, starts at the x-axis at minus 360, then goes above, rotates, comes back to it, touches it again, but then the shape isn't exactly the same after that, because it doesn't just go up again, it goes down. So the graph hasn't yet repeated, and then goes down, and then finally, once it's at 0, meaning 360 degrees after the beginning, then it touches the x-axis again and continues going up. Therefore, the period of sine theta is 360 degrees. Then we can look at the graph for cos theta. That's the graph for the cosine function. And since, as we just saw, since they're co-functions, the overall graph will have the exact same shape, except there'll be an offset of 90 degrees. So while the sine function starts at a value of 0, like you can see in this graph, the cosine function has a value of 0 and continues above the x-axis 90 degrees earlier. But besides that, the overall shape of the graph is exactly the same, and therefore the period of cos theta is also 360 degrees. And we can also look at the graph of tan. So it's a little different from how cos and sine look, and it's what you get when you divide sine theta by cos theta by the quotient rule. So since it's a combination of sine and cos, both of which have a period of 360 degrees, you think, then shouldn't tan theta also have a period of 360 degrees? Well, turns out, not really. When you draw the graph of tan theta, what you end up seeing is that its period is actually 180 degrees. So after every 180 degrees, the graph keeps repeating itself. You can look at it over here. So from minus 270, it starts at a value of negative infinity. And then it increases and increases and then crosses the x-axis halfway after 90 degrees, and then keeps increasing and eventually has an asymptote up to infinity at minus 90 degrees, meaning 90 degrees after cutting the x-axis, after which it comes back from negative infinity at the bottom again and repeats this whole pattern. Therefore, the period of tan theta is 180 degrees. So going back to the question in the example, so they asked, what is the value of theta in the interval of 0 to 360 degrees? So they want these two values. So by the simple calculation we've done so far, we've got the 30 degrees already. Then how do we get this value of 150 degrees? We'll do that using the 4 quadrants. This is the diagram of the 4 quadrants, and here's the basic idea. So each quarter represents a certain range of angle values, and each quarter is called a quadrant. So So it starts at the top right over here with the first quadrant representing an angle of 0 to 90 degrees. Then the second quadrant represents an angle of 90 to 180 degrees. The third quadrant is 180 to 270 degrees, and the fourth quadrant is 270 to 360 degrees. Then, based on which quadrant you're looking at, there's a certain set of rules you have to follow to find out the angle in that quadrant. And those rules are the ones written out here in blue. So I'll demonstrate how the whole thing works using the same example of sine theta is equal to 0, 5. So how you'd go about determining the 150 degrees is as follows. First, you start by determining the reference angle. So the reference angle is an acute angle, meaning an angle with a value between 0 and 90 degrees. And that also implies it has to be a positive value. So we'll see in a few of the later examples that when you do the sine inverse of the value, you sometimes get a negative value. And then even if it's less than 90, say something like negative 80 degrees, it's still less than 0. So it doesn't follow this rule of being between 90 and 0 degrees. In the case when you get a negative angle, when you do the inverse function, you just turn it positive. Luckily in this case, we just got a positive value of 30 degrees. But if it was negative 30, your reference angle would just be a value of 30 degrees. But coming back to this example, when we did sine inverse of 0, 5, we got 30 degrees as the reference angle. So that's always the first step. Apply the inverse function and determine the reference angle. Then the second step is notice the sign of the function value. So in this question, it said sine theta is equal to 0, 5. When I say function value, I just mean whatever value comes on the right that is equal to the function. So in this case, it's 0, 5, meaning it's a positive value. Cool. So we have our reference angle and we know that the function has a positive value. Then we go to the third step, which is check in which quadrants the function has that sign, meaning in which quadrants does the function have a positive value. And you do that using the abbreviation ASTC. And a good way to remember it is from the phrase, all students take calculus, ASTC. And what each of the letters means is, it refers to which trig functions in that quadrant have a positive value. So in the first quadrant, A stands for all, meaning all trig functions have a positive value in the first quadrant, meaning sine, cos or tan of any angle between 0 and 90 degrees will have a positive value. Then S means that only the sine function will give a positive value for any angle between 90 and 180 degrees. And that's kind of indicated through the way the functions are represented over here, where you can see both cos and tan theta have a negative in front of them, but sine theta doesn't. And you should remember that theta is this reference angle, meaning this acute angle. So the angle between 0 and 90 degrees. Therefore, just sine theta or just cos theta or just tan theta by themselves all have a positive value, since in the first quadrant they're all positive. So then the sign in front of them indicates what happens to the overall function. So sine of a value between 90 and 180 degrees would have the exact same value as sine of that angle in the first quadrant. And then cos of an angle between 90 and 180 will have the exact same value as cos theta in the first quadrant except negative. And the same for tan theta. And a way to represent any angle between 90 and 180 is by saying 180 minus acute angle theta. Meaning you can get any of the angle values between 90 and 180 by saying 180 minus an acute angle falling between 0 and 90 degrees. So that's kind of what the terms in the brackets represent in each of these quadrants. So in the third quadrant, you can get any angle between 180 and 270 degrees by saying 180 plus acute angle theta from the first quadrant. And in the third quadrant, the t implies that only the tan function will have a positive value, which can be seen over here. And sine and cos both have negatives in front of them. And lastly, for the fourth quadrant, any value between 270 and 360 can be determined by saying 360 minus acute angle theta. And the C stands for cos. So cos is the only function that will give a positive value for an angle falling between 270 and 360 degrees. And it will have the exact same value as cos of the acute angle theta in the first quadrant. So coming back to the third step, we know our reference angle theta is 30 degrees, and we know our function is sine and it's positive. And then by the third step, we check in which quadrants the function has a positive sign. And from abbreviation ASTC, we can tell that it will be positive in the first quadrant where all functions have a positive sign, and it will be positive in the second quadrant where only sine has a positive value. Then we go to the fourth and final step, which is determine the other angles by learning and applying the quadrant rules. And what are the quadrant rules? They're the equations we see in the left side terms in these brackets. So in the first quadrant, the bracket on the left side functions, if there was one, would just have a theta in it. So the quadrant rule for the first quadrant is just theta stays as is. Then the quadrant rule for the second quadrant is 180 degrees minus theta. For the third quadrant rule is 180 degrees plus theta. And finally, for the fourth quadrant, the quadrant rule is 360 degrees minus theta, as summarized down here. So in this case, since we know that the function is positive in only the first and the second quadrants, we'll just apply the quadrant rules for those two. Therefore, the first angle that satisfies sine theta is equal to 0,5 is the first quadrant angle, meaning theta is equal to 30. And then the second angle that satisfies this is that which you get from applying the second quadrant rule, which is 180 degrees minus theta, giving a value of 150 degrees. And since in the question they asked only for values in the range of 0 to 360 degrees, we've got all the answers for the question. You may have noticed for the first quadrant there's an extra 360 in there. This one. So this quadrant rule of 360 plus theta would be used in the case when they asked for a range with an angle greater than 360. So say if they had said what values of theta would solve the equation sine theta is equal to 0,5 in the range of 0 to 500 degrees. In that case, then you'd also go like, okay, the first angle is just a reference angle, 30. Then we would check the second quadrant angle, 180 minus 30, 150. Then we'll be like, okay, we've seen all the values in 0 up to 360. Then we have to determine any values greater than 360. Then you'd come back to this rule where you say 360 plus 30, giving a value of 390 degrees as well. And that is where this rule comes in. But under normal circumstances, you'd just be asked up to 360 degrees. So it would just be this theta rule and these rules for the other three quadrants. But yeah, anyway, to finally answer the question, the values of theta in the interval of 0 to 360 degrees that would satisfy sine theta is equal to 0,5 are 30 degrees and 150 degrees. Let's look at another example.